So moving on to question 10. Says particle undergoes simple harmonic motion and the maximum energy is E max and amplitude is A x naught. The particle is released from rest and its maximum displacement amplitude. What is the change in the kinetic energy when the particle has traveled a distance of that much? Okay, so when it was over here, and this is x0 and this is negative x naught, when it has traveled third of x naught, so that means this is 1, 2, does that mean it's here or here? When it says when the particle has traveled that much. So time is 0, initially starts from there, okay? This is x naught over 3. This is 2x naught over 3, and this is 3x naught over 3, which is x naught. So Killian, are you there? Hello?
Yeah, I'm there.
So what is the change? The question is, what is the change in the kinetic energy when the particle has traveled distance of that? So the question is it here or is it here? Red or blue? All right, so I think it'll be here when it has traveled x naught over 3, right? It's because the distance from there to there is x naught over 3. So the total energy is equal to half, we know this equation, m omega squared x naught squared, right? That's the total energy given by this formula sheet. Right here, that one there, right? M omega squared x naught. So that's the energy there. And then when it's over here, the energy is the potential energy, the spring potential energy, because it's still stretched. It'll be half m omega squared and then 2x naught over 3 squared, true? So this will be half. This will be 4 on 9 at the front, 4 on 9. So this is the E max. This is 4 on 9, half m omega squared x naught squared. So this will be 4/9 of the E max. So therefore the kinetic energy would be E max minus this one. Very similar to the previous question that we did, you know, 5/9 E max, isn't it? So it had 0 kinetic energy here, but then now when it's there, it's moving that way. And that energy is simply the difference between the total energy and the remaining potential energy, right? Because the total energy is always the potential energy plus the kinetic energy, true? So just minus that, that from that, you get the kinetic energy. So I think the answer is C. Question 10, I think it's C. Yep. Moving on. It's like the one I'm showing you over here. Okay. Now moving on to this one here. A body moves with a simple harmonic motion with period t. Total energy is this. What is the total energy when the period of the motion is changed to 5t and the amplitude of the motion remains constant? All right. So total energy when the period, so it's going a little bit faster. So period is changed to 5t. It's actually going slower, right? Slower.
Yeah.
And so total energy is equal to how much? Total energy is equal to half m omega squared x naught squared, right? Now we know that omega is equal to 2 pi over t, and it's also square root of k over m, isn't it?
Yeah.
That's what we need to understand. But the thing is that when the period, we don't need to know this at the moment. So when we plug that here, that's equal to half Mass is staying the same. This is 4 pi square over t square, because if you plug that in there, then you get that. And then this is the x naught square, right?
Yeah.
And this is our, let's say this is our E total. Now, what is our new energy? So ET dash, I'm going to call that the new energy. And this will be half m 4 pi square over. This is now 5t square, isn't it? The new amplitude is, the new period is 5t now. So that substitute all that in here. And the amplitude is now going to be, the amplitude of the motion remains constant. Okay, so amplitude is, so not everything is staying the same. The only change is that one, okay?
Yeah.
Now this will then become 5 squared is 25, right? So 25, 1 on 25 at the front. And it'll be, everything else will be just the same, you know, 4 pi square t square. You know, 5 square is 25 there, t square is t squared there, and then x naught square. And that bit there is simply the original ET. So this will be 1/25th of the ET. So it'll be the, all right, what's 1 on 25? It's 1 over 25 is the same as 0.04. So I think the answer is A there.
Okay. Yeah.
So you're getting it, right?
Mm-hmm.
So A. Okay, no problem. Now moving on to 12. 12. Moving on to 12. A source of sound moves away from an observer. Observer frequency of the sound differs from the frequency emitted by the source because, very simple, I think. We know that the speed of sound stay the same, right? So C and D are ruled out.
Mm-hmm. It's going to be away from the observer, so less, isn't it? Yeah.
So want to go for A? Okay, let's double check. So A12 is B.
Oh.
Okay, so just have to draw a diagram for this. So you have so you have something like this, right?
Right. Yeah, that makes sense.
And there's the observer, and it's moving away from you. So it's so wavelength over here is increased, right?
Mm-hmm.
Yeah, so wavelength is greater. So if wavelength goes up, then the frequency should go down, true?
True.
The reason for that is the speed of sound, speed of wave is the wavelength times by frequency, and this one is staying the same, right? This is constant. If this goes up, this has to go down in order to maintain its constancy. Now moving on to 13. All right, radiation is incident on a single rectangular slit. The diffracted beam that emerges from the slit is incident on a screen. The slit width is doubled and the wavelength of the radiation is also doubled. The intensity of the radiation remains the same. Which of the following correctly describes the angular width of the central maximum of the diffracted beam and the total number of photons incident every second on the screen? Okay. So we have this circular aperture, and through that, some radiation is coming out of that. So I'm just going to write it like this. That's the slit width there, and then you have this diffraction pattern, you know?
Yeah.
And we have the Rayleigh criteria of the square is just lambda over d, and this is the slit width, you know?
Mm-hmm.
And also, let's just have a look at that formula for the single slit. So single slit is, oh, there you go. Yeah, that's exactly the Rayleigh criteria formula, isn't it? So they have it in B, doesn't matter. So that's our B or D, whatever, you know. And what it says is that in the question is that so there's a light coming through, the slit width is double, so D is going to become 2D, and the wavelength of the radiation is also double, so lambda is going to become 2 lambda. So the angle is so what that angle tells you is, so when you use this formula in the single slit, that's the angle. That's the angle to the first. Hold on, I think it's either that or all of that. Okay, but anyway, we'll come back to it later. Hold on, I think the formula is for the single slit. So D, let me just work it out. D sine theta is equal to yeah, I think that angle is just this one here, not the entire thing. So it's the angle from the central maximum to the first minima. That's that formula there, okay? So obviously there's not gonna be any change to the theta, right? Because it's gonna be 2 lambda over 2D, so 2 cancel out, so it's still gonna be lambda over D, you know? So this angle, the distance from the angle from the first, the central maxima to the first minima is not gonna change at all. So angular width of the central maxima, I think the answer is unchanged.
Yeah.
But the number of photons incident every second on the screen. So this is something that we haven't covered yet. All right. It says the intensity of the radiation remains the same, right?
Yeah.
That's the clue. But the thing is, intensity is like the amount of energy that is incident on the screen. So you might be tempted to go for unchanged, right? But I think the answer is C. Let's double check. The answer is C, that's right. So the reason for that is, so the angle unchanged. What about the number of photons? So this is something that we haven't done yet. So photon is, so when you have red light versus the blue light, when we study quantum mechanics, we find this formula, energy is equal to hf over lambda, or hc over lambda, sorry, or hf. So this is energy of each photon. So what that means is red light has small frequency, less frequency compared to blue light. Red light has greater wavelength compared to the blue light, longer wavelength, right? So when you plug that into this formula here, h is a Planck's constant, all this equation is saying that red light is made up of small particles, small photons. They have less energy. Whereas blue light has bigger particles, bigger photons, simply because they have the same, what is it? The same. No, they don't. So they have this. They have higher frequency, right? This is lower frequency. So that's smaller particle. That's bigger particles, right? Now, when it comes, let me just try to explain this with some analogies. So if you have 1,000 kilogram worth of people, and let's say it's made up of children, okay? So each children weigh, let's say 20 kilogram. Then if you divide the 1,000 kilogram by 20 kilogram, 20 kilogram, then you get how much? You get 50. You get 50 children, right? But if you have 1,000 kilogram and worth of people, and you divide by adults, let's say adults weigh 60 kilogram on average, or let's say 50 kilogram on average, then you end up with 20 adults, right?
Yeah.
So what that means is that in this question, the amount of energy, the intensity stays the same. That's what it's saying, right? The intensity stays the same. But you used to have the wavelength is increased, right? From lambda to 2 lambda. That means you went from blue light to the red light. That means you went from adults to children. See?
Yeah.
So you end up with more particles arriving. So for example, let's say the intensity is 100 joules per second, but then the red light is 1 joule is worth 1 joule, and blue light is worth 2 joules.
Mm-hmm.
Then you have 100 particles, 100 photons. Here you have 50 photons, right? If your wavelength is doubled, that means you increase your wavelength. It's as if you're going from blue to red. Number of photons has increased from 50 to 100, right?
Yeah.
That's what it's talking about. So that's a difficult one to understand. All right, I think we should call it a day here, right?
Yeah.
So
Thanks
next
for that. Could you
lesson. So I'll send you the recording, okay?